so we are discussing when your final is going to be. The last day of classes is Thursday, November the 16th. We don't have class on Thursdays. So it has been requested. Let me put this up on the right screen so that other people can see it. There we go. It has been requested by Mr. Finch that our final on this class be on Wednesday the 15th. That would also be my personal preference because I know that I have to make out the Circuits 1 final by the 13th here. And so for my workload and sanity thing, it would be better if this test, if I didn't have to work on 2 tests at the same time because I will die. So my principal concern would be the amount of material that I'm supposed to cover in this class. So we're going to talk about parallel resonance today, and then we're going to look at other resonant forms and effectively how to make things that aren't simply a series RLC circuit or a parallel RLC circuit look like one of those so that we don't have to do a ton of terrifying differential equations in order to figure out what our bandwidth, U factor, and all that kind of stuff is. After we cover that, we're going to talk about frequency and magnitude scaling of circuits, which will lead us into filter design. And then after that point, I'm supposed to talk about H parameters, F parameters, and all that kind of good stuff for 2-port networks. Probably not going to get to the 2-port network stuff at all, which means when we need it for electronics 2 in the spring, I will just have to go through that part quickly so that it makes sense. Won't be that big. So first, let me ask, is Wednesday the 15th? I have one person requesting it. I see several other thumbs up. Okay, so it seems like the general consensus is either Wednesday the 15th or I don't care. So if nobody is opposed, then let's put the exam on Wednesday the 15th. Yes, North.
How would the take-home portion work?
Fantastic question. So I can try to get the take-home portion of the test up on the 13th, make it due officially by the 17th at 5 p.m., which is when the quarter is officially over, and then accidentally forget to take points off as long as you turn it in before the 20th when your grades are due, which is a pretty common thing that I've done for my take-home tests if you've had me before. I officially cannot make anything due after the quarter is over. Unofficially, I can accept it without penalty until a point where I say this is the cutoff. So does that non-answer technically answer your question? Okay, so that's how we'll take care of that thing. That also requires me to actually get the take-home portion done in a timely manner and not a week after. But that's on me, not on you guys by any stretch of imagination. All right, so I think I'm going to have plenty of material to talk about getting through just resonance, filter design, and all of that kind of stuff that lasts us through until the 13th. But if for whatever reason I finish that portion of things early, we would just have a review day. Does that sound like an unreasonable thing? So we'll stop after we get into filter design, and that'll be the end of circuits 3. All right. Any other? Yes.
So beginning before you said we have roughly 12 homeworks.
Yeah, it's going to be. So I need to finish up a homework set on transfer functions and Bode plots. Then there will be a homework set on resonance, and that's probably going to be about it. Yeah, so I'm not going to just hit you with 6 homework assignments over the next 2 weeks. You would die, I would die, nobody would have any fun. I need to talk to my graders and see how annoyed they would be with yeah, because I don't grade them, so let me make sure that they're not going to be too pissed off about that. If they're not, then I'm open to it. I'll just put it there. North.
How many design projects
are you going to have? 3. So there are 2 that are already up. Then there will be a design project on filter design. The only reason that it isn't up is because we haven't covered filter design yet, but I actually have that one made out. So
when would that project?
It'll be due officially at the end of the quarter. unofficially, if you get it in before grades are due, I'm okay. Pretty much, yes. That being said, design project 1, if it takes you more than 30 minutes, you're doing it very wrong. Design project 2, also, if it takes you more than 30 minutes. No, I mean, so for design project 2, you're told where you need your pole and your zero to be. So just pick a value for the resistor and then do the math to figure out what capacitor values you need. Yeah, and then chain that crap together. Why does it have to be harder than that?
You overestimate my ability.
Okay, well, yeah. I mean, I give you a transfer function that has a single zero and a single pole, and I tell you, if you do this, this is how you get a pole. If you do this other thing, this is how you get a zero. Pick a resistor value, let's say 10 kilo ohms, and then and then go from there. Yeah, and then if it happens to work out that you're not scaling, like you don't wind up getting the right magnitude thing, put a third stage in there that just gives you a gain of whatever it needs to get to that with no phase angle. So that would just be a resistor biased op amp network, probably let's see, from where I put I gave you 1 pole and 1 zero, so the negative sign should cancel out there. So you would have a positive signal, so you would use a non-inverting amplifier if you needed to scale. There we go. That sentence just did a third of your design problem. All right. Any other questions before we do, what we're supposed to do today? All right. I'm going to assume that the talking that isn't directed at me means no. So let me get this junk out of the way. I need to double check something here really quickly because I think I might have accidentally included a square term that wasn't supposed to be there. So let me just check. It'll be. Nope, I only had it in my notes. I didn't have it here. So in my notes, I accidentally had that this term was squared, but it should not have been squared. So I must have either not been paying attention or realized I made the mistake of whatever. All right. So when we finished our last lecture, we had just worked this example problem, and we found that the voltage drop across our capacitor and the voltage drop across our inductor both had a magnitude of 600 volts at resonance, and we talked about why this might be a problem. Another simple question here is, and bear with me, if we have a 10-volt drop across our source and a 3 ohm resistance there, and we know that at resonance our current is 10/3 of an amp, what's the voltage drop across our 3 ohm resistor? Well, it's also 10 volts. This is the opposite polarity of the source. Then we have a 600 volt drop in magnitude here and a 600 volt drop in magnitude there. Is Kirchhoff's voltage law satisfied in the system? That's a trick question. It has to be. It's the law of conservation of energy. The reason why it's appearing like it isn't satisfied is because we only looked at the magnitude. We did not look at the phase angle at all. What we would actually see if we were looking at the phase angle would be that these two voltages are 180 degrees out of phase. So while the capacitor does experience a very large voltage and the inductor does experience a very large voltage, they happen to cancel each other out, which of course makes sense because the impedances of those two things cancel each other out. The very last thing that I mentioned to you guys was that 600 volts here, so the voltage that we see at resonance, isn't technically the largest voltage that our capacitor would experience in this system. So let's look at that very briefly before we get into parallel resonance. So let me scroll down here. So for our circuit, and let me redraw it here because it's no longer on the screen. We had a source voltage, a resistance, the impedance of our inductor, the impedance of our capacitor, and we're just going to look at the voltage drop across the capacitor here. Okay. So this will be VC. That is not Q omega L, that is a shittily drawn J. Because we're just dealing with impedances. All right, so if I wanted to find the voltage drop across my capacitor in this circuit, I, being a lazy person, would just use voltage division because that would make it pretty simple, right? So using voltage division, we could see that VC would just be our source voltage VS, whatever it happens to be, times 1 over J omega C divided by R plus J omega L plus 1 over J omega C. And then I would multiply through by a factor of J omega C over J omega C because I don't like fractions inside of fractions. In doing that, we would find that we would have our source voltage VS multiplied by 1 over 1 minus omega squared LC, so that's our real part, plus J omega RC. And from this, the magnitude of our capacitor voltage would simply be the magnitude of our source voltage divided by the square root of 1 minus omega squared LC plus omega RC quantity squared. This guy should be squared as well. So what we're going to do is we're going to take the derivative of this voltage and set it equal to 0 to figure out what frequency corresponds with the maximum value of our magnitude. Plug that frequency back in and find out what our maximum voltage would actually be, right? So scroll down here. The derivative of the magnitude of our capacitor voltage with respect to omega as to equal 0, solving this and trying to not bore you with the math, we would find that omega maximum, so the angular frequency at which VC is at its maximum, is given by the square root of 1 over LC minus 1/2 R over L quantity squared. Well, 1 over LC is nothing more than omega naught squared. And then we have 1/2 times omega naught over Q quantity squared. Factoring out omega naught, this is going to look like omega naught times the square root of 1 minus 1 over 2Q squared, which is approximately omega naught for large values of Q. So realistically, our capacitor voltage will hit its maximum at a frequency that is slightly lower than omega naught, right? And as Q goes up and up and up, the contribution of this second term gets smaller and smaller and smaller so that it's looking more and more like square root of 1 minus 0. So for extremely high values of Q, we find that our capacitor voltage hits its maximum at omega naught, and that the maximum value of that capacitor voltage is simply Q times our source voltage, right? For our particular example, plugging in the Q factor of 60, we would actually see that the maximum voltage drop across our capacitor is like 601.25 volts, right? So it's a very, very small increase over the exact value that we got when we excited the circuit at our resonant frequency. Okay. So what does this tell us conceptually? Not a whole heck of a lot, except that when we're drawing our Bode plots for a system like this, actually that peak value that we see for our resonance should be shifted very slightly lower than omega naught. And depending on the value of Q, depends on how far we would shift it to the left, right? So for very high values of Q, we could put it right at omega naught, and that would be fairly accurate. For very low values of Q, it would actually be shifted to the left some. All right, so now let's talk about resonance. We're going to go through this fairly quickly because we're going to see that it is extraordinarily similar to the series resonance case that we've already looked at. So let me write parallel resonance first. So let's consider a simple parallel RLC network. So we have some resistance here in parallel with some inductance L in parallel with some capacitance C. This is part of a greater circuit. Let's call this voltage V, the voltage drop over the whole thing, this current I, current flowing through the whole network. And we're going to do something that I don't know that we have done to this point. Instead of looking at impedance, we're going to look at admittance, because that'll be a little bit easier on us since everything is in parallel. Okay. So the input admittance of this network, Yn as a function of j omega, is going to look like the admittance of the resistor, which is just 1 over R, right? Because admittance is just the reciprocal of impedance. The impedance of a resistor is R, so the admittance of a resistor is 1 over R. Talked about this in circuits too. Then we're going to have 1 over j omega L, and then we're going to have plus j omega C, right? So I'm using admittance here just because when I have 3 things in parallel, I can add their admittances up like they were in series, and it's going to make the math look practically exactly like what we saw for our series RLC circuit, except that we're using the reciprocals of everything. Okay. I can lump together my imaginary terms, and so this would give me 1 over R plus J times omega C minus 1 over omega L. And once again, we should observe that our resonant frequency occurs when the imaginary part of this admittance goes to 0, right? So in order for resonance to occur, we need omega C to be equal to 1 over omega L, which occurs when omega is equal to the square root of 1 over LC, and we call this omega naught. So the resonant frequency for a parallel RLC circuit is the exact same thing as the resonant frequency for a series RLC circuit. And that should hopefully make a little bit of sense to you guys, because when we looked at transient analysis of series RLC circuits and parallel RLC circuits way back in circuits 2, omega naught didn't change even if we went from a series combination to a parallel combination. So it shouldn't change here either because it literally represents the exact same thing. So if we looked at the admittance as a function of frequency, here's omega. Let's put omega naught here in the middle. This is the magnitude of yn as a function of j omega. We should see that at the resonant frequency, our admittance hits the minimum. So it's going to look something like this, where this minimum value is 1 over r. Another way to think about this would be to flip this graph upside down. At our resonant frequency, our impedance should be at its maximum value. And looking at our phase angle as a function of frequency, so putting omega naught smack dab in the center yet again, here's positive 90 degrees, here's negative 90 degrees. We see that we're going to get something that looks like this, which are essentially supposed to be the exact same graphs that we saw for our series RLC circuit, except that now we're looking at the admittance. So we can see then very clearly that the admittance of our network is dominated by the inductor for very low frequencies. It's dominated by the resistance around our resonant frequency, and then is dominated by the capacitor for very high frequencies, which is exactly inverse of what we saw for a series RLC circuit, which once again should make perfect sense because we're just looking at the reciprocals of everything. Okay. So now let's take a moment and derive what our Q factor should be for a parallel RLC network. Okay. We're going to do this very similarly to how we did it for our series RLC network. We're going to look at a system which is excited at its resonant frequency and contains some resistance R in parallel with some inductance L in parallel with some capacitance C. Like so. Let's say that IS of T is equal to IM cosine omega naught T. So we're explicitly exciting this thing at the resonant frequency. And we're going to do our analysis in the frequency domain because we all know that analysis in the time domain sucks. So we shouldn't do it. So this is going to look like IM angle 0 degrees amps. In parallel with R. In parallel with J omega L. In parallel with 1 over J omega C. We are going to determine the energy stored by our capacitor. So I'm going to define this voltage as VC. We're also going to have to find the energy stored by our inductor. So I'm going to define this current as IL. So the first thing that we're going to solve for is the voltage drop across our capacitor at resonance, right? So at the resonant frequency, the admittance of our inductor and the admittance of our capacitor completely cancel each other out, which means instead of looking like a short circuit, these guys are going to look like an open circuit. So all of our source current is going to flow through our resistor. And so we should see very easily that VC is just IS times R, which is going to look like R times IM with a phase angle of 0 degrees. And therefore, our capacitor voltage as a function of time is going to be R times IM cosine omega naught T measured in volts. Yes. So at resonance, that represents when our admittance is at its minimum, which in turn represents when our impedance is at its maximum. Okay. So at the resonant frequency, let me scroll up here. At the resonant frequency, these two terms, which are admittances, cancel each other out, right? So the J term we're going to have as an admittance 1 over R plus J0. What's the reciprocal of 0? Infinity, right? Which is why they're going to look like an open circuit at resonance. So we have defined our capacitor, or actually we haven't defined it. We have determined our capacitor voltage. Now we can easily determine what our energy stored by our capacitor is. So that's going to be WC as a function of time is 1/2 times our capacitance times the voltage drop across our capacitance squared, or 1/2 C multiplied by IMR cosine omega naught T quantity squared, which is going to look like IM squared R squared C divided by 2 times the cosine of cosine squared, excuse me, of omega naught T. Because this is energy that would be measured in joules. To find the current flowing through our inductor, I'm just going to use Ohm's law because I know the voltage drop over everything because everything is in parallel. So using Ohm's law, our inductor current, IL, is just going to be VC times, no, excuse me, divided by J omega naught L, right? So I is equal to V over Z. So that's going to be 1 over J omega naught L times R times IM with an angle of 0 degrees. And so that is going to look like IM times R over omega naught L with an angle of negative 90 degrees. Which in the time domain, we could represent as IMR divided by omega naught L sine omega naught T. The energy stored by our inductor is 1/2 L times the derivative, or excuse me, not times the derivative, times our inductor current squared. So that's 1/2 L times this IMR over omega naught L sine omega naught t quantity squared. So I'm going to have Im squared r squared. I'm going to have an L in my numerator and an L squared in my denominator. So I'm just going to leave me with just an L in my denominator. So let's see here. This is going to look like twice omega naught L times the sine squared of omega naught t. Sorry, I should have omega naught squared here. Apologies for that. Since we know that omega naught squared is equal to 1 over LC, that would be like putting an LC in the numerator. The L's would cancel each other out, and I would have a C up here. So I could write this as equivalent to Im squared r squared C divided by 2 times the sine squared of omega naught t. Okay. So just to be clear, I'm putting an LC here to get rid of the omega naught squared down there. This L cancels this L, and all I'm left with is Im squared r squared C divided by 2, which is the exact same magnitude I see for my capacitor stored energy. Now I'm going to add those two guys together. So our total stored energy is going to be WC plus WL. Since sine squared plus cosine squared is equal to 1, this comes out to be a constant value, just like we saw on Wednesday, of Im squared r squared C divided by a factor of 2. So this is the energy storage part of our definition of Q. We can call this W capital S because it's constant. To find our energy dissipated per cycle, that is going to be the integral over one period of the power absorbed by our resistor. The power absorbed by our resistor can be expressed as the voltage drop across our resistor squared divided by the resistor value. So VC of T quantity squared divided by R, which is going to look like the integral from 0 to T of 1 over R times Im R cosine omega naught T quantity squared dt. I heard whisperings. You guys got a question? What is that subscript? R, because it's the power absorbed by a resistor. Yes. So, to put it bluntly, no. Let me explain why. We know that there is no average power absorbed by capacitors or inductors. That's really what we're dealing with here. Right, so the average power absorbed by a capacitor over any number of cycles is 0. The average power absorbed by an inductor over any number of cycles is also 0. Could you energy dissipated by the resistor in one cycle? So capital WS is our energy stored. Capital WD is our energy dissipated, because our quality factor is a ratio of the stored energy to the dissipated energy multiplied by a factor of 2 pi, which we'll get to in just a moment. All right, so again, using my circuits one trig identities and all that kind of stuff. When I square this cosine term, I'm gonna get a factor of 1/2 and all that kind of jazz. The integral over the cosine of twice omega t part is gonna go to 0 because I'm integrating over an integer number of periods. And so what I get left with is 1/2 Im squared times r times capital T, which is the period of our waveform. That is equal to 2 pi over omega naught. And so this becomes 2 pi times Im squared times r divided by twice omega naught. Yes, I am well aware that the 2's are going to cancel each other out, but I'm going to leave them in there and you'll see why in a moment. Our quality factor Q for this parallel RLC circuit is 2 pi times WS over WD. So that is going to look like 2 pi times, let me scroll up here so I can get it. Im squared r squared c, all divided by 2. So that's RWS. WD comes down here. 2 pi Im squared r over twice omega naught. This 2 pi cancels this 2 pi. This Im squared cancels this Im squared. This 2 cancels this 2. R squared divided by r gets rid of that guy. And what we are left with is simply omega naught RC. This omega naught RC is literally the reciprocal of the Q factor that we got for a series RLC circuit. And we could mathematically manipulate this to find that we could express our quality factor as R times the square root of C over L. Once again, the reciprocal of one of our representations for Q for a series RLC circuit, and also R over omega naught L. Again, the reciprocal of what we saw for a series RLC circuit. So these are our 3 different forms of Q for a parallel RLC circuit. They are all identical, so we just use whichever one makes the most sense for what information that we have. So going along with what we did in class last Wednesday, now let's derive, so let me scroll up here so you guys can see this part. Let's derive the transfer function for this system and see how things are going to shake out for its frequency response. So starting with a system in the frequency domain where we would have some input current waveform flowing into a network containing a resistance and impedance, J omega L, and an impedance 1 over J omega C. Like so, I'm going to define the output signal for this system to be the voltage drop across all of these elements in parallel. And the easiest way for me to relate the input current to the output voltage for this system is to just use Ohm's law and deal with the admittances. Okay. So I can say that V out is just equal to I in divided by Y in. This is just Ohm's law, yes, sir. This circuit's not. Not particularly, no, because we're going to use it generally speaking to figure out how it behaves over all frequencies. And then effectively, we're going to put everything in terms of omega naught and Q, just like we did in our last class meeting. So this is going to look like IN divided by 1 over R plus J times omega C minus 1 over omega L. I'm just using the expression for the admittance that we derived at the very beginning when we were talking about parallel resonance. Much like I did last time, I am going to multiply and divide the imaginary part of this by Q. One other thing that I'm going to do to get it into a form that's familiar is I'm going to multiply by R over R to get rid of this 1 over R bit here so that it looks pretty. So the impact that's going to have is that in my numerator, I'm now going to have R times IN divided by 1 plus JQ times omega RC over Q minus R over omega Q, like so, recalling that Q is equal to omega naught RC and equivalently R over omega naught L allows me to write this as R times IN divided by 1 plus JQ times omega over omega naught minus omega naught over omega. And at this point, we are effectively identical to what we had for our series RLC circuit, except that there's a factor of R in the numerator. So our transfer function here, which in this case will be defined as the output voltage divided by the input current, is just R divided by 1 plus JQ times omega over omega naught minus omega naught over omega. Sorry, I scrolled too far there. The magnitude of H of J omega is then going to be R divided by the square root of 1 plus Q squared omega over omega naught minus omega naught over omega quantity squared. And the square root goes over this whole thing. And our phase angle as a function of J omega is the inverse tangent of negative Q times omega over omega naught minus omega naught over omega. So our magnitude response effectively looks identical, except that we have a factor of R in the numerator. Our phase response is literally the exact same thing. For those of you that are wondering where the hell the R went, it winds up being R divided by R, which cancels out. And that's why the phase response is the same. All right. So what are our half power frequencies for this thing going to be? Okay, so when we had our series RLC circuit, we had a ratio of voltage to voltage. And so we were looking at when it was 1 divided by the square root of 2. Our half power frequency is going to be, in this case, whenever we have R divided by the square root of 2, because that's going to be exactly 3 decibels lower than our peak value, right? So the peak value, or the numerator, was 1 for the series RLC case. It's R for the parallel RLC case. But it's going to happen at the exact same condition. We need Q squared times omega over omega naught minus omega naught over omega quantity squared to just be equal to 1. So let me write that out. Our half power frequencies will occur when the magnitude of h of j omega is equal to r divided by the square root of 2. So it's always the peak value divided by root 2. This occurs when Q times omega naught over omega. Sorry, I have that backwards. Omega over omega naught minus omega naught over omega is equal to plus or minus 1. This is the exact condition that we were dealing with previously. So our omega low should be the exact same thing. Omega naught times negative 1 over 2q plus root of 1 over 2q quantity squared plus 1. Omega high will be omega naught times positive 1 over 2q plus the square root of 1 over 2q quantity squared plus 1. And our bandwidth is omega high minus omega low is just omega naught over q. So our relationships for our resonant frequency are the same. Our low frequency cutoff and high frequency cutoff are the same. Our bandwidths are the same in terms of omega naught and q, right? So our bandwidth for our parallel RLC circuit is just going to be 1 over RC. The bandwidth for our series RLC circuit is just going to be R over L. All right. Any questions before we move on from this? So now let's talk about other resonant forms. So what we've talked about to this point are idealized cases, right? So we have the simplest combination of elements possible. We have simply a series RLC circuit or a parallel RLC circuit. Much like when we were dealing with these in circuits 2, this represented about as simple as it could get, but we are often going to be faced with systems that don't fall into one of those 2 easy buckets to put them in. Unlike circuits 2, I'm not going to make you guys write huge, terrifying algebraic relationships involving second order differential equations in order to figure out what to do. Okay? So if we were to look at a real parallel RLC circuit, let's start with that. We might mathematically model it using the following circuit. So I'm going to call this resistor R2, and I'll talk about it, what it represents in a moment. And here I'm going to have some inductance L. And then some resistance R1. Once again, I'll talk about what it represents shortly. And then over here, I have my capacitance C. Okay. So resistance R1 in this case represents the ohmic core and radiation losses of our coil L. So effectively what that means is that a real inductor, the coil is going to heat up. So we are going to have some ohmic losses that are represented usually by resistance, because we know that resistors convert electrical energy into heat energy. We also have core losses. So what that means is effectively whenever we have an inductance with a ferromagnetic core, when we excite this at a sinusoidal frequency, we are going to be causing the magnetic dipole moments of the ferromagnetic core to align and then disalign with each other, and this requires energy. We need to represent the losses that are incurred as we magnetize and demagnetize this core over and over and over. And then our radiation losses represent the fact that we might not have a toroidal coil or something like that. And so we might have electromagnetic flux that's leaving our system. That is also a loss we represent with some resistance. So this is just a lump parameter of several different physical things that happen to coils when we sinusoidally excite them in a practical system. Okay. R2 represents the dielectric losses of the capacitor. So effectively, it can heat up as well. The resistance of our wires and any intentional resistance added to the system, meaning we physically put a resistor in the circuit. So that's what R2 is representing. Now, let me ask you guys what I hope is a really simple question. Can we do any element combination techniques here to make this simple? How would inductance in series with a resistance look like a capacitance? I don't follow your logic.
Oh, I wasn't saying that.
Okay.
In previous examples, it's kind of lumped them as a undistinguished and non-distinguished.
Okay, but if we have an undistinguished, so what you're saying is a generic impedance. Okay, so would a generic impedance necessarily be valid over all frequencies? No. So therein lies our problem. This is as simple as of a model as we could possibly get that is valid over all frequencies. So what we're going to have to do to simplify this thing is effectively develop relationships that are only valid over our frequency band of interest. And then we will wind up having a representation that looks something like this, which would simply be some equivalent resistance. And I'm just going to call this R sub E. I'm not using REQ because I don't want it to come off like we're just doing resistor combination, because we certainly are not. Okay. In parallel with some inductance L sub E. And then in parallel with some capacitance C sub E. So this is our ultimate goal, would be a simplified form that looks like either a parallel RLC circuit or a series RLC circuit because we know how those behave. So that's our ultimate goal. So consider the two networks shown here, okay? So drawing a line here to let us know that we're now working on how to get from that first representation to that second representation, okay? So let's say that I have the following network where I have a resistance R sub S, where the subscript S is simply for series, in series with a reactance J sub XS. And it does not matter in any way, shape, or form whether this reactance is provided by an inductance or a capacitance. Okay? So the sign on this, we're assuming it to be positive. If it were negative because we were dealing with a capacitor, we would literally just replace X sub S with negative X sub S and it'll all come out in the wash. Okay. Over here on the right, I'm going to have a parallel representation where I would have R sub P, where in this case, the P subscript simply denotes we're going to be in parallel. With some parallel reactance, J sub X of P. Looking into the terminals, we can define then a series admittance Y sub S. Looking into these terminals, we could define a parallel admittance Y sub P. And what we are going to be doing is simply developing a transform that lets us go back and forth between these two forms. If I scroll up here, we can see pretty easily that if there was a way for me to have this middle branch look like a parallel combination of a resistor and something, I could lump those two resistors together and I would have a parallel RLC network. Similarly, if I had a series RLC network with a branch that contained elements in parallel, if I could convert that parallel branch into a series branch, I should be able to lump things together as well and make it look like a series RLC network. So that is our ultimate goal. So there are a few conditions that we need in order for this to work. And the first is that the quality factor Q of each of these networks has to be the same. So in order for these to be electrically equivalent to each other, Q has to be equivalent between the two forms as well. I'm going to have you guys do this for a homework assignment, but I'm going to give you the answer right now. The series Q factor is just going to be the magnitude of our reactance divided by our resistance. And you can derive the parallel Q factor to be, oh, what the hell happened there? Sorry. The parallel resistance divided by the magnitude of the parallel reactance. Just as a quick aside here and to help you guys think about things, what do you think the resonant frequency of this series thing is going to be? Whatever frequency makes JXS look like 0, right? So if XS represented a inductance, we would have R over L, or negative R over L, right? It's just a first order circuit now. If it were a capacitance, we would have RC. Same thing over here. Simple stuff you guys have done before, way back in circuits 1. You're just trying to, effectively, you want to make this thing look like a short circuit. So whatever Frequency causes this thing to, yes, and then this guy to look like an open circuit, and then you calculate your Q based on that. So because we're doing Q at resonance. All right. So under these constraints, we could say that our series admittance is just going to be 1 over RS plus JXS is going to look like RS minus JXS over RS squared plus XS squared. To be clear, the only step that you have to do to get from here to here is multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. And because we need YS to be equivalent to Y sub P, Y sub P is just going to be 1 over RP minus J one over XP. Double check to make sure that minus sign is correct here. Let me think about this for just a second. Oh, yeah, sorry. Total brain fart here. I'm trying to figure out where that minus sign comes from. We would have 1 over RP and then 1 over JXP, add those together, but 1 over J looks like negative J in the numerator. That's right. Sorry about that. All right. So making this guy right here equivalent to this guy right here, we can effectively establish a transform such that R sub P would be equal to R sub S squared plus X sub S squared divided by R sub S and X sub S, excuse me, X sub P is equal to R sub S squared plus X sub S squared divided by X sub S. If we were to get the ratio of RP over XP, we could see hopefully very easily that this just comes out to X sub S over R sub S. And this can be simplified such that R sub P could be expressed as R sub S times 1 plus our quality factor squared. And X sub P could be expressed as x sub s times 1 plus 1 over our quality factor squared, which will become approximately r sub s times q squared for large Q. According to the textbook, large Q is any Q that is greater than 5. X sub P will approximately be X sub S for large Q. And this means that CP is approximately equal to CS, or LP is approximately equal to LS. And so now we have a transform that allows us to make that series branch look like a parallel branch and combine things, or vice versa. So when we get back in class on Monday, we'll work a couple of examples utilizing these transforms and all of that kind of good stuff. And then that'll lead us specifically into magnitude and frequency scaling and all that kind of good stuff so that we can get into filter design. All right. You guys have a great rest of your day. Have a good and safe weekend and all that kind of jazz. And I'll see you on Monday.